In the previous video, we learned about the quantity discount model. The scenario one, the first scenario, and that was when the carrying cost was fixed, was not actually dependent on the price. So for that, we learned how to solve the problem. We solved the example. Now we want to see the second scenario in which the carrying cost actually is dependent on the price. So it's going to change based on the price. The second scenario in the quantity discount model is when the carrying cost is a percentage of price. So this means that H is not going to be a fixed value. It's going to be depending on the price. And since this is a discount model, that means that based on the range that you're going to get based on different quantity that you're going to get different price range, you're going to also get different carrying cost. So let's see how this works, the second scenario. When carrying costs are expressed as a percentage of price, so that means that the carrying cost would vary and change with the price. Determining the best purchase quantity, the optimal quantity QP, Q optimal, can be actually found with the following procedure. Step 1, beginning with the lowest unit price. Compute the minimum of points for each price range until you find a feasible minimum point. This means that until a minimum point falls in the quantity range for each price. This is going to make more sense when we do an example. So bear with me so far. After step 2, we do a step second. In a step second, if the minimum point that you found in a step 1 is not the lowest unit price, then to find the optimal order quantity, you need to also compare the total cost of the minimum point that you found in part 1 and compare that with the total cost of any lower prices that you have. The quantity that would make the smallest, the minimum total cost, that would gives us the optimal quantity order. So let's see an example. Here is the example. Surge Electric uses 4,000 toggle switches a year. Switches are priced as follows. If they purchase between 1 and 499, the price would be 90 cents each. If they purchase between 500 to 999, the price would be 85 cents each. And if they purchase 1,000 and more than that, the price would be 80 cents each. It costs approximately $30 to prepare an order and receive toggles. So that's the S here. And the carrying costs are 40% of purchase price per unit on an annual basis. Determine the optimal order quantity and the total annual cost. So you get the formula here. The total cost is equal to the carrying cost plus order cost plus purchasing cost. Purchasing cost is going to be dependent on the amount of order. And you have also the formula for the optimal quantity after you figure out using the procedure that we learned. So one quick note here is that this is the carrying cost here is a percentage of purchase price. So this means that the carrying cost of the toggles depends on the price, which means that it depends on the quantity that you order. So if they order between 1 and 499, which they're gonna get a price range of 90 cents each, then the carrying cost would be 40% multiplied by 90 cents, which is 36 cents. So the carrying cost would be 36 cents. But if they order between 500 and 1999, then the price that it would be 85 cents, and the carrying cost would be 40% of 85 cents, which would be 34 cents. and so on and so forth. So it's going to be also different if they purchase more than thousands. They're going to get 80 cents each. So the carrying cost would be 40% of 80 cents, which is 32 cents. All right, so now please pause, work on this problem, try to solve it using the procedure that we talked about. And after you are done, come back to see a solution. All right, so let's solve this problem. Before we go ahead and solve this problem, we need to figure out age to do a pre-solving step, which is, as you see here, this table, to figure out age, because age depends on the price, so it's going to be a percentage of price. So we need to, because we have different ranges and different quantity ranges and discounts for that with different price, we're gonna have different age. So let's go ahead and fill out this table. So based on the problem, it says that if they purchase between 1 and 499 toggles, they're gonna get a price of 90 cents per toggle. So that would be 0.90. And H would be, the carrying cost would be 40% of that, which is 40% of 90 cents. So that would be 40% of 90 cents, which is 36 cents. The next range is if they purchase between 500 and 999, they're going to get a discount of 5 cents, so the price would be 85 cents. And carrying cost would be 40% of that, so that would be 40% of 85 cents, which is 34 cents. And the last range is if they purchase 1,000 toggles or more, they're going to get another 5 cents discount, so the price would be 80 cents each. And the carrying cost would be 40% of that, which is 32 cents. All right, so now we need to start from the lowest price range, which is 80 cents here. So we're going to find the carrying cost here, which is 32 cents. And we're going to use the formula to find the optimal quantity. So that would be the optimal quantity for the price range of 80 cents. And the formula is 2 multiplied by D multiplied by S divided by H. Now if we plug in the numbers that we have, that's 2 multiplied by 4,000, which is the demand for 1 year, multiplied by S, which is $30, divided by H, which is 32 cents. Here, 32 cents, so that would be divided by 0.32. Right? Because these values, this is in dollar, so we put this as dollar as well, so that would be 0.32. Now, if we do the math, the quantity will be equal to 866. So this is the quantity, but we need to check, do they get 80% or 80 cents each for if they purchase a quantity of 866? So we're gonna see if this will actually match here, which it doesn't, because for the price of 80 cents to get, they need to purchase at least 1,000 or more. And 866 is not greater than 1,000. It's not within the range, within this range. So this is actually not a feasible solution. Not feasible. So this is not feasible. So what should we do? We're gonna go to the next price range, which is 85 cents. And for 85 cents, the carrying cost is 34 cents. So we're gonna find the Q for 85 cents. So we're gonna do the math again. We're gonna plug in the numbers. The number is going to be all the same except for the carrying cost, H. H would be different. H would be 34 cents here. So the denominator would be 0.34, and this would be 2 multiplied by 4,000 multiplied by 30. And if you do the math, the quantity that you will get is 840. 840. So now we need to check whether this 840 quantity is actually feasible. This means that at this quantity, is the price 34 cents? The carrying cost is 34 cents. And we're gonna check it here. Is 840 between 500 and 999? Yes, it is. So this is feasible. Okay. So we find the quantity that is feasible, but because this quantity is not at the lowest price is 80 cents and this is at 85 cents. So we need to do the second step. We need to find the total cost when Q is for the smallest one, which is at least 1,000. At the thousands, they're gonna get the lowest price range, which is 80 cents. And we're going to compare that with the total cost of the quantity that we found here, which is 840. So we're going to compute the total cost for Q equal to 1,000 and Q equal to 40. Whichever is the lowest, that quantity would be our optimal quantity to order. So here is the neater and cleaner version of, or typed version of the solution that we have done so far. For the lowest price, 80 cents, we solved for the Q optimal, and that was 866, which is not feasible. It's not greater than 1,000, so it's not 80 cents. So this is not feasible. And then we're gonna solve it for 85 cents, the next lowest price. And at 85 cents, the carrying cost is 34 cents here. And the value that we found is 840, which is between this range. So it's an acceptable, a feasible one. So the next step is to find the total cost for 840, and because it is not the lowest price range, we still have a lower one, 80 cents. We're going to also find the total cost when Q is 1,000. So compare the total cost of Q equal to 1,000 and total cost of Q equal to 840, whichever is the smallest, that's going to be our optimal. Step 2 for this problem is to find the total cost for the two for the Q that we have, which is 840, and also for the lowest range price lower than whatever 840 is. So 840 is at the price range of 885 cents. Lower than that is at the price range of 880 cents, and that would be the quantity of 1,000 and more. So we're gonna also compute the total cost for Q equal to thousands. And you see the total cost formula here. So if we plug in everything in this for Q equal to 840, we're gonna get 840 divided by 2 multiplied by Q, which multiplied by H, the carrying cost, which is 34 cents, plus D divided by Q, which is 4,000 divided by 840 multiplied by S, which is $30, plus P multiplied by D. P is 85 cents and D is 4,000. So if we do the math, the total cost when Q is 840 is $3,684. If we do the math for total cost equal to, for total cost when Q is 1000 into this using this formula here. So that would be Q divided by 2. So that 1000 divided by 2 multiplied by H. H here is 40% of 80 cents. So that would be 32 cents. Plus D divided by Q. So that's 4000 divided by 1000 multiplied by S. So multiplied by 30. Plus P multiplied by D. P is 80 cents multiplied by 4000. And if we do the math, the total cost would be $3,480. If we compare that to the other cost, we see that the 3,480, which is for Q equal to 1000, is a smaller one. So this means that the optimal quantity to order is 1000 for us in this problem. We can also, if we plot the total cost curve for this problem, because we're going to have different price ranges, we're going to have different actually curve here as well. So if they order between 0 and 500, the total cost will be this part here. And that would be at the price of 90 cents each. If they order between 500 and 1000, the price range would be 85 cents, and the total cost curve would be this one. And if they order more than 1000, the total cost curve would be this one at the price of 80 cents. So now the point that we found using the formula is it was 840, which is this one here, which the total cost would be this point right here, which is 3,684. But if we actually look at, because we are minimizing the total cost, which is on the y-axis, so the minimum of total cost here would be right here. This would be the total minimum total cost, which Q equal to 1000. So from the curve also, the plot, we can actually easily, by eyeballing, figure out which one would be the minimum, which would cause the minimum cost. And that would be our optimal quantity. So the optimal quantity would be 1000.